Hello guys, welcome back. So in today's video, we'll see how to quickly derive the delta-y transformation. So this will be very useful in your exams in saving time, and also you needn't memorize all the formulas. Although there is easier way to remember all these formulas with some techniques, I would still prefer going on from the basics. So if you know how to derive this easily and quickly with the basics, you needn't memorize anything at all. So anyway, going into the derivation, if you see, I have put it in such a form that it is looking like a two-port network, right? So now what we will do is we will try to see them separately. So here we have, this is the delta structure and this is the y structure. So we are going to derive the relationship between them using just the Thevenin theorem. So to go from delta to y, what we are going to do is we are going to see the look and impedance from input and output for both structures. And since they are equivalent, they should be equal, right? So let me put it here. So let us take the input impedance. So these both should be equal. So what is it here? It is R1 in parallel with R2 plus R3. If you notice, I'm opening A bar and B bar. Here also it is open. So once it is open, this R2 directly comes in parallel with R3. So this look and impedance is R1 in parallel with R2 plus R3 divided by R1 plus R2 plus R3. Good. So this is equal to, what is this side? Since this is open, RC will not come into picture. This look and impedance is just RA plus RB. Okay. So this is RA plus RB. So now I'll just simplify the left hand side. So this is R1 R2 plus R1 R3 by R1 plus R2 plus R3. Similarly, this side it is RA plus RB. So now same thing we'll do it looking in from the output with input open. Okay. So what will it be? Here it is R2 in parallel with R1 plus R3, right? So R2 in parallel with R1 plus R3. R2 plus R1 plus R3. This is equal to, what is it here? It is just RA plus RC. So RA plus RC. So here it is, if you have to simplify this, R1 R2 plus R2 R3 divided by R1 plus R2 plus R3. So this is equal to my RA plus RC. So these are the two equations we got, right? So now can you try to compare what is the term common in the right hand side? RA is common. So if you look this side, what is the term common? Denominator is same, right? Numerator, what is common? My R1 R2 is common. So from this only I can directly write my RA is nothing but R1 R2 by R1 plus R2 plus R3. And then the remaining terms will be respectively RB and RC. So RB is R1 R3 by R1 plus R2 plus R3. Similarly, RC is R2 R3 by R1 plus R2 plus R3. So now if you take this equation and revisit this thing, so let me put it here. Usually the way they remember is, whatever RA is here, it is nothing but the product of the adjacent resistors divided by the sum of all three resistors. So for RA it is R1 R2 by R1 plus R2 plus R3. For RB it is R1 R3 by R1 plus R2 plus R3. And for RC it is R2 R3 by R1 plus R2 plus R3. Okay, this completes for my delta to y. Good enough, very quickly we solved it, not even 3 minutes. Okay, now let us also see for y to delta. So here the only difference, okay, I'll just copy this one. So here the only difference we are going to do is, when we are looking in the impedance, Thevenin equivalent, we are going to short the other side. So in the previous one, we used to leave it open. Now we are shorting it. So let us try to get the input impedance. So for this side, what is it? It is R1 in parallel with R3, right? So here again, instead of going with resistance, we'll try to take the conductance. So we'll see the net G, okay? So R1 in parallel with R3 is nothing but G1 plus G3, right? If my resistors are in parallel, my conductance will be the addition, okay? And why have we left out R2? Because R2 is coming in parallel with a short. So effectively this is like a short only. Okay, now looking the net conductance here, what is it? So this one is shorted, right? So which means that my RA and RC are coming in parallel. When I look from A across A and B, RA, RC are parallel, and then RB is in series. So for conductance, RA, RC in parallel is nothing but it becomes GA plus GC. And then it is coming in series with GB, right? So how do I write it? GB into GA plus GC by GB plus GA plus GC, correct? Because in series, my conductance, I have to take it similar to whatever the resistance were in parallel, the same formula for parallel combination of resistances. So this is one equation. So the next equation, I will look from the output. So from A bar, B bar side. So net G from here, and here again I have to short the input. Okay. So now what is the effective conductance looking in from here? Here R2 is there. R1 anyway goes away because of the short. So R3 is in parallel with R2. So it is G2 plus G3. And this is equal to this side what I have. This side again I have to short this and look from here. So here RA, RB are in parallel. So it is like GA plus GB. And RC is in series with this. So GC into GA plus GB divided by GC plus GA plus GB. So if you have to write it out, it is GA GB plus GB GC by GA plus GB plus GC. And here it is GA GC plus GB GC by GA plus GB plus GC. Right? Now if you observe left hand side and right hand side, your G3 is common in the left hand side. And right hand side the denominator is same. Numerator what is common? GB GC is common. So you can straightly write out your G3 is nothing but GB GC by GA plus GB plus GC. So if you want to write in terms of resistances, you can easily convert. So before that, we'll also write out GB and G2 and G1. So G2 is GA GC by GA plus GB plus GC. Similarly, your G1 is nothing but GA GB by GA plus GB plus GC. So from here, if you want to find R3, it is nothing but 1 over G3, right? So it will be GA plus GB plus GC by GB GC. And this again you can write as 1 by RA, 1 by RB, 1 by RC. So then you will get 1 by RA plus 1 by RB plus 1 by RC divided by 1 by RA RC. Sorry, RB RC. So this is nothing but RB RC plus RA RC plus RA RB by RA. Right? Similarly, my R2 will be 1 by this thing, and if you finally derive it, what you will get? The numerator is going to be same here. If you observe in the previous case, your denominator was same. Here if you observe, your numerator is same. Why? Because in your conductance term, your denominator is same. So in your resistance term, your numerator is going to be same. So here you will get the same numerator. So RA RB plus RB RC plus RC RA divided by whatever is left out in my numerator. So RB is left out here. Here if you see, GA was left out, RA I am writing. Similarly, your R1 is same numerator divided by RC. Okay. So this also easily you got. And what is the easy way to remember this one? So here you are going from Y to delta, right? So if you are going from Y to delta, you need to find R1, R2, R3. So R1 is nothing but your numerator is going to remain same. It is just the product of these RA, RB, RC taken two at a time divided by whatever is not adjacent to R1. So R1, the denominator is RC if you observe, and for R2 it is RB, and for R3 it is RA. So it is sum of product of two of them taken at a time divided by the opposite, directly opposite resistor value. So in terms of conductance, what it is, if you see G1 is nothing but product of adjacent terms divided by the sum of all the conductances. Similarly for G2 also product of adjacent conductance divided by sum of all three. Similarly for G3 also. So if you observe the formula, this is the same thing we said for resistances in Y to delta or delta to Y, right? So resistances in delta to Y is same as conductance in Y to delta. So this is how you quickly derive, and if you want to remember also, you can remember it this way easily. And here also you needn't actually remember which one to go for when you're converting from delta to Y. So let's say take the case of this thing. Let's say I want to go from delta to Y. So R1, R2, R3 are given. I want to find RA, RB, RC. So I don't know whether I have to go with open circuit case or short circuit case. So the only thing I need to observe is in which case my RA, RB, RC are coming as sum in the natural form without any denominator and other complications. So if I see in open circuit case, it directly comes as RA plus RB. But if I short it, my RA comes in parallel with RC. So I should not use the short circuit case. I should directly go to the open circuit case. Similarly, if I have to go from Y to delta, now I need to find R1. So in which case my R1 appears natural form. So in the open circuit case, if I go, it comes as R1 plus R, or rather R1 comes as parallel with R2 plus R3. So it is like R1 plus R2 R3 by R2 plus R3. Or sorry, it is like R1 into R2 plus R3 by R1 plus R2 plus R3. So if you see here, my R1 is not coming in a separate case. It is actually multiplied with something else. So you should actually not go with the open circuit case approach. If you short circuit it, then what happens? It is just R1 parallel R3. So it is just R1. It is just 1 over R1 R3 by R1 plus R3. This is nothing but in your conductance, it is G1 plus G3. Directly you can get. Here, however, the direct form of G1 plus G3 or G1 plus G2 is not possible. So this also you can quickly find. You needn't memorize which approach to use for which. So if you know the concepts and you're clear with your basics, you can quickly derive, and once you derive also, let's say you derive for 2 or 3 times, you forget, and without going back to the formula you actually derive it, you will be actually able to remember it for longer duration than if you just go and check the formula, because you're actually putting in some effort to get that result, right? So your brain will definitely remember it for a longer time. So I hope this video was useful for you guys. Take care. Bye bye.